next few days. So we're going to get warmed up today, and then we'll do a little bit of it today, and then more tomorrow, then maybe more the day after, and then it'll take maybe 2 to 3 days to work it all out completely. Okay, so let's start with the following question. Random math trivia. Let's say, as you know, I'm very fond of my parentheses, even though you're not, and that's your loss. So if I gave you a little bucket of parentheses, the question is, and let's assume that I'm going to give you, I always only write matched parentheses. So I give you a bucket of matched parentheses. The question is, how many different kinds of parenthesized expressions can you create? So if I give you a bucket that contains just one matched pair, right? The only thing you can do is create that. Okay. If I give you a bucket with 2 matched pairs, how many shapes do you think you could create?
2.
What are the 2? Okay, so we can do this and we can do this. Right? Okay. So if I give you 1, you have 1. If I give you 2, you have 2. Okay? Yeah?
Could we do like open, not like, I was thinking like where they're like kind of shifted within each other.
Yeah, but they're indistinguishable, right? I don't discriminate between my parentheses. So this like flipping that around doesn't make any difference. Yeah?
So are you just looking for the power set of each set of parentheses?
I don't know. You're going to tell me. Okay? So now, supposing I give you 3 pairs of parentheses, how many different parenthetical, well-formed parenthetical expressions can you create? That's the critical thing. What can you not do? Okay.
Leave one hanging.
Okay, you can't leave them hanging. Yeah, you can't leave them hanging. Okay. So, I want you to come back and tell me what you can do with 3 pairs of parentheses. Go, talk to your neighbors.
Oh, got it.
But 1, 2, 3, 1 through 2 are all the same.
Okay, so for 3 pairs of parentheses, how many answers do we have? How many different expressions? Yell out a number. 4, 5, 6, 6. Okay, let's start with our 4s. Give me your 4.
All 3.
So just say left, right. Call it out.
Left, right.
Left,
Right,
right.
left, left, right.
Okay?
Wait, there's only 3.
Okay. I'm just writing what you said. Okay. All right. Okay, next.
Left, right, left, right. Right, or left, right. Left, right.
Uh-huh.
Left, right.
Okay, there's your 4. Anybody else spot any others? Yeah.
Left, right, right.
Any others? Oi, where are the 6ers?
I'm getting close.
We're writing all of them out.
Oh, yeah.
Oh, you want us to figure out
Okay. Anyone else spot one that's missing? I don't think you will. Okay, you better not. Okay, so when we get to 3, we have 5. Okay? All right, so now, when we have 4, go.
So that's that you can either, oh, well, you can also take them and only put one on each side, so that's another 5 or 5.
I know you guys probably had it.
Are you literally the first half problem?
So you put it on the left, right, but it's going to be
So that's another.
yeah, but like sometimes you don't get paid. So like the third option.
And then the other stuff.
And when on the bottom one, like if you put it on the outside, that's different than putting it on the inside.
Okay. In 5, 4, 3, 2, 1. We're back. So, you think you're going to succeed at doing this by enumerating every single one of them by hand, like methodically? Probably not. How could you have gotten from the 2 case to the 3 case? Yeah.
Put it on the left, on the right, and around, like because you have an extra.
Yeah, so basically you've got all of the ways of doing the 2s, right? And each of those gives you a way of doing the 3s. And then you have like the one other option that doesn't come directly from that, right? Essentially this one, right? So essentially what you need is you need a way of going from the smaller answer to the bigger answer, right? You will probably run out of time if I asked you to make you do all the enumerations for 4, and if you don't, I can assure you will for 5. Okay? So this is not a math class, so I'm not going to teach you how to derive a formula for these, but there is actually a very nice property. It turns out that these things are called Catalan numbers. Okay? This is not a political statement. I'm not making any statements about the nature of the Spanish Federation. They're called that because they were invented by a French mathematician named Eugène Catalan. So they're called Catalan numbers. And basically the Catalan numbers are Catalan of 1 is 1, Catalan of 2 is 2, Catalan of 3 is 5, Catalan of 4 is actually 14, Catalan of 5 is the answer to the universe, 42. And so it grows quite a bit. Okay? So what I want to do today is I want to talk a little bit about calculating Catalan numbers. Not because I am that interested, I actually am, because they're parenthetical and cute and all that. But less because I'm interested in computing them and more because they will help me illustrate a point. So let's do this now. I wanted to go. All right. So, I know what I wanted to do. I wanted to display control. Yeah. Okay. All right. So, here is a formula for calculating Catalan. Here's a program that calculates the Catalan numbers. Okay? And if I run this program, it comes back and gives me my answer. Okay? So, that's the way you calculate Catalan numbers. And it's in the book, and if you want to read the formula and try to figure out exactly why this formula does it, I invite you to do that. And if you don't care about combinatorics, well, you don't care about combinatorics, and it's just fine too. Okay, so this is a formula that's going to give you this answer. Okay, all right. So let's try Catalan of maybe 6. Any ideas? Anyone know their Catalan sequences? Not that well. Okay. Okay. So far, so good. Catalan of 10. Oh, it's taking a little while. Seems to be taking quite a while, doesn't it? Definitely taking a while. Okay, so the question is, why does it take so long to compute the Catalan numbers? Okay. So this is a place where it is helpful to use this tool that you've seen before. Okay, let me put it here. So remember Tracer? Yes? Anyone using Tracer? Ah, excellent, good. A small number of virtuous people. Okay, so let's do the following. Let's run, let me actually get rid of some of these. Let's just have this one, okay? So let's run this and look at what the trace looks like. So I'm going to trace this, and I know it's not the most readable thing, but it'll become pretty relevant. Like there's going to be a shape argument I'm trying to make, and that's all that really matters. So what happens here? When I ask for a Catalan of 5, which is 42, well, I compute the range and then I do the fold. Okay? So when I do the fold, we need to compute a whole bunch of values. Well, Catalan of 0 is 1. That's just by lookup. Okay? Catalan of 4 is 14. Catalan of 1 is 1. Catalan of 3 is 5. Catalan of 2 is 2. Catalan of 2 is 2. Catalan of 3 is 5. Catalan of 1 is 1. And so on. Okay? So now if I go down and look at this, well, there's going to be another fold in there, right? And this is the same Catalan of 2 that I asked for over here. And this Catalan of 2 has a fold in here. But if I go look at this Catalan of 2 in here, it has the same fold in here, and so on and so forth, okay? So what's going on is there is a huge amount of repeated calculation. Right? We're just calculating the same thing over and over and over again. We go off and compute Catalan of 3, which requires computing Catalan of 2. And when we try to compute Catalan of 2, we have this fold, which ends up looking... Is this going to look familiar? Why is it going to look familiar? It's going to look exactly like this tree over here, which also looks exactly like this tree over here. Right? So we keep computing the same sub-expressions and the sub-expressions and the sub-expressions and sub-expressions, sub-expressions, sub-expressions over and over and over again. Okay? This turns out to be a general problem you run into in computer science. There are many applications, and I will show you at least some of them. You will do at least one of them for homework, but there's many, many, many applications in computer science where you're trying to solve a big problem, you decompose it into smaller problems, but the smaller problems keep showing up over and over. I picked Catalan not because it's an interesting computer science issue, but because it very nicely illustrates the problem for us. Okay? Very nicely illustrates this difficulty that we're going to recompute the same thing over and over again. And so what you would really like to be able to do is remember the value so you don't have to compute it again. Okay? So, now you can probably guess why I'm doing this in the context of the state part of the course, because what we'd like to do is we'd like to change something to say, we have computed this answer before, let's not compute it all over again. Does that make sense? That's what we want to be able to do. Okay, now, that's the game plan here. Okay? Now, before I do that, let me do this. Let me copy this. Okay, so this is code we saw before, right? We had a box, and we could make a cell. We put a box in there. We hold on the old value, update it. And when we run this, what is the output? I want you to stare at this board for a moment. And before I hit run, tell me what sequence of values I'm going to see printed out on the right. Talk to your neighbors. Talk to your neighbors. Go. Okay, everyone, yell it out. What do you expect to see?
0, 1, 0, 1, 2, 3.
Wow, that's good. Okay, it's like we got a jazz beat going here. Okay, good. Okay, so 0, 1, 0, 1, 2, 3. Okay? So this 2, 3 came because we went back to C1 and it remembers, and that's that whole closure business. Okay? All right, now I'm going to show you a different way, a slightly different way of writing the same thing. Okay? You have not yet been, if you've programmed in languages like Java or Python, it turns out there's actually two kinds of state. And I've shown you one kind of state, and I'm going to show you the other kind of state. The exact differences between these are actually rather subtle. It's actually a thing that I discuss in CS 173. For our purposes, we probably won't need the detailed distinction. the point is, you don't necessarily have to create a data structure, right? You could just have said something like b is equal to 0, right? Hold on to the value of b, and now you want to say b is equal to something like that. Okay? So initially b was 0, and now you're updating b to be the old value of b plus 1. Okay? And you hold on to the old value and print old val. Okay? So this is the kind of thing you're trying to write, except it looks kind of really weird. It looks really weird because I just said b equals b plus 1. And that doesn't, b can't be b plus 1, right? We're trying to say something slightly different than that. We're not saying b equals b plus 1. We're trying to say change b to be b plus 1. Okay? So if I just try running this, it's going to say, well, first of all, you just already declared b. Are you trying to declare b again? Like, you can't declare, you've already declared it. What are you trying to do? Okay? You can't have two b's in the same place. We're not trying to declare a new b. By the way, in some languages, this will actually make a new b, and lots of fun ensues when you're doing that. But what we're trying to say is change b. So in Pirate, the syntax is I want to change the b. This is saying change b to be whatever b was before, add 1 to it, and change the value of b. Okay? Make sense? Well, this isn't going to run either, because it's going to say, wait a minute, you told me b equals 0, but apparently you don't want it to be equal to 0. You want it to keep changing. So the problem is if I read b equals 0, I might read the rest of my code and think b is 0, and in fact it's not going to be 0 all the time. Okay? So in Pirate, what you say is you say var. Var says b is a variable. It's a thing whose value can vary. So if you see var b equals 0, that's a hint to readers, including yourself, saying don't assume b is always going to be 0. It's only initially 0. It might change over time. Okay? Yes?
So how is this different from ref?
Ref is a way, so ref is what you put for fields. Var is what you put for variables. Okay? And now, this program works perfectly, and we don't need this box data structure anymore. Okay? There's various subtle differences between bars and refs. That's why they're two different keywords. And the exact semantic details of that, it has to do with the aliasing and what optimizations, like what a compiler can optimize and what it can't, etc. It's really outside the scope of 19, so I'm not going to say much more than that. Okay? But it'll be convenient for us to just be able to use this instead. Okay? Good? Okay. And also partly I wanted to show you this. I don't need this. I could have just used boxes for the rest of the semester. But I want to show you this because when you go to other programming languages, for those who haven't programmed or programmed much before, you go to other languages, there are two different notions. There is being able to change the value of a field versus being able to change the value of a variable, and they're really quite different ideas, even though in many languages you use the same syntax for both of them. Okay? Yes, question?
If you were to just up in the lambda just return b, would it be also show like the warning signs type?
No, that's a great question. Because when you say, if I said b over here, what I'm returning is the value that's associated with b. The value itself is just a value, right? Now, if I returned a box value, that would show you a warning sign. But the value itself isn't just a value, it's just a constant, right? Like 3 is not, there's no warning sign for 3, right? Because 3 is just 3, it's not going to change, okay? So the value doesn't change, so it's actually a subtle difference. That's one of the ways in which refs and bars are different. Refs, the value itself can change. With var, the variable changes, but the value associated with it is whatever it is. It could be mutable or immutable. Make sense? Yeah. Yeah.
So do we no longer need the block?
Oh no. Oh no. We're doing 3 things, man. Right? We're doing 3 different things. We're doing 2 things. We're binding a name, and then we're changing a value and returning the old value. So we need to say, do this, then do this, and this thing's value I don't really care about. This is the only thing whose value I care about. So you really need the block. Okay? Good. Okay, questions so far? Yes?
Does line 5 return something then?
And if it does, we won't know. So maybe it does, maybe it doesn't. So let's explore this, okay? So let's create a var, v is equal to 0, so v. Now I'm going to say v is equal to v plus 1, okay? And, well, so if I say v, it's now 1. So what's actually happening is in Pirate, everything returns something, so it actually returns like a special nothing value. And it also doesn't print nothing values, so you have no way of telling. Okay? Okay. Okay, good. All right, so, clear enough? We're good? Okay, so what I want to do is I want to get back to my Catalan numbers, which I think I've now completely successfully wiped out, haven't I? No, I have not. Okay. Okay. So let me do this under CPU for now. All right. So Catalan of 5 is 42, and if we try to run Catalan of 13 or so, it's taking a while, right? So that's pretty bad. Okay. That's the thing we want to optimize and see if we can make it any faster by remembering the old value. Okay, so first of all, observe that I need this pattern we've seen before, right? If I put the memory inside the Catalan function, that would be like the counter, putting the counter, the memory of the counter inside the counter function. If it gets created every time, then nothing gets remembered, right? So we had this critical pattern where we had the mutable thing outside the lambda, and the lambda was the thing that we actually returned, so that every time you called this lambda, it was referring to the same mutable box or the same variable, right? That's a critical pattern that we need. So the first thing I'm going to do is I'm going to rewrite Catalan to say Catalan is just a value, and it's equal to this lambda. Okay? All right? So far, so good? Is this going to run? Yeah?
Your checkbook is
Remember rec? Okay. Okay. Fun is a short form for, so if I say fun f of something, something, end, that is the same internally in Pirate. It gets converted to rec f equals lambda. Okay? So fun is just a short form for that. We could remove fun from the language and everything would work fine. You just have to write this pattern every time. Okay? And if you're curious to see what's really going on with rec, make sure you don't go early for Thanksgiving. Okay. That's Wednesday's lecture, Wednesday of Thanksgiving. That's what it's about. Okay, good. So, our program still works. That's good. Okay. Now, what I need is I need a, you remember in what was this thing called? Oh, MapReduce. MapReduce, remember you looked at key value pairs, right? I have some key and it's associated with some value and I can look up by the key and I get a value. I need something like that, okay? So I'm gonna make myself a data type called memory, okay? And it has an in and an out. So given this, essentially what I'm trying to say is, given this input, what was the corresponding output? That's what I want to remember, right? So far so good? Okay. So, initially, my memory is, I don't have anything to remember because I haven't seen any calls yet. Yeah? Good? All right. So now what happens is, I get an actual call. That's not going to work. So, okay, so I haven't seen any calls yet. So and also let's keep running this to make sure we didn't screw anything up. Okay, when I say we, I mean I, but of course I don't mind sharing the blame. So if you don't pay attention and say, hey Sriram, like that's your fault too. Okay, pair programming, and I've got like how many pairs do I have here? Like 65 pairs. So I would expect a high degree of competence in the room. So. Right? So what we want to know is, when we get an n, we want to know, have we seen this n before? Right? Because if we've seen the n before, we're good. If we haven't seen the n before, that's a problem. Right? So, here's what I would like you to do. I'd like you to spend a minute with your partner writing a function that's going to take a value like n. It's going to take a list of values. In this case, it's going to be a list of mem elements, right? And comes back and tells me either that the value is there and here's the corresponding right-hand side, or no, the value is not there. Hint, what do you think the type of this function is? There's going to be an option involved, right? It's going to say a none saying I didn't find it, or some and this is the corresponding value. Go.
I would have done the thinking about it. It's actually really good. So you can like give us some and then you can still repeat it. There's some like there's like all these people and there's like not so if you like a full 2 wow like you or like there's a lot of combinations. Yeah. Like I'm thinking full while and it should be yeah, well, you I mean they go
I would use the dictionary.
Okay, 5, 4, 3, 2, 1. We're back. Okay, people have a thought on how to do this? This is the kind of function I expect you to be able to write at this point. So, where's my screen? Oh, there we go. Okay, good. So, this is going to be a block because we're going to have to do stuff. Some of you may know there's a built-in function called find that does that. So, how do we call find? What is the signature of find? How many parameters does it take? How many parameters does find take? How many parameters do you expect find to take? 2. What does one of them have to be? It has to be the list. Which list are you trying to find it in? What's the other parameter?
What are you trying to find?
Huh? What are you trying to find? You think it's a value? No, that's in high school, man. You're not in high school anymore. So what's it going to be? It's going to be a function. So here's what we're going to do. We're going to write that function, right? So that function is going to iterate over every element and come back with a Boolean saying, is this the element you're looking for, right? So we're going to take an element of the memory and we're going to ask whether what? Great. Okay? And we're doing it over which memory? Okay? So that's the result of running find over the memory list. It's going to come back and tell me whether the value is there or not. Okay? What is the data type? It's going to return an option. Okay? It's either going to be a sum, it's going to either be a none, or it's going to be a sum of some answer. Okay? Okay. What do we do if we get back a sum?
Return it.
That's our answer. We've already computed it before, so we don't need to do anything more. That's it, right? That's the whole answer. Right? So I will put this as the first line. Okay? Otherwise, what do we do now? Yeah?
Compute the value.
Compute it. We're going to have to do all of that stuff. Okay? And what?
And store it.
And store it. Not just enough to compute it, we also have to store it. Okay? And return it. Oh my God, the number of things. Okay. Okay, so let's do this. Are we up for this? We're up for this? Okay? I need all of your eyes, all right? Because this is easy to get wrong. Yes.
Shouldn't the answer that out?
Yeah.
What is ants over here? It's the element that matched that predicate. But every element of the list is? Okay? So it needs to be answer dot out. Okay? All right. So now we're ready to compute the the actual answer. Okay? I'll call it this. Okay? Okay, so it's this, otherwise this, otherwise this, otherwise this. Okay? Yep? Okay. So, we have to compute that answer. We now have to, what? Store it. Talk to your neighbor, and then come back and tell me what code I'm going to write to store it. Go.
You want memory equals memory is link of actual link of mem and actual into
Yes.
Is there a name for it?
Assign.
Or colon equals.
All right. 5, 4, 3, 2, 1. We're back. Who wants to read out some code to me? Read out some code. Read out some code. Read out some code. Read out some code. Go.
Memory.
Are you still done, by the way, with your Catalan, your 6th one? Ooh, oh, I know. Put on my course evals. Go ahead. Yeah. Okay.
Memory. Colon equals memory. Link. Sorry. Link. Mem. N. Oh, sorry. Actual. I didn't realize I typed it so fast. What?
No, you wrote it.
And actual.
And comma actual.
Sorry. And then comma memory.
Like that?
Yeah.
And then an end.
Everyone okay with that? Okay. So, what we're saying is the input is n, the output is whatever actual computed. Link those together and add that to the memory. Okay? Yeah, so let's make sure we understand. So that's our updated memory. It's all the stuff we had before, plus this one new entry. Okay? That's how we're remembering a new value. And then we have to return what? Memory? Actual. Right? That's the value. Okay? Put this on a different line just so we can see the three things that are going on.
All functions
Okay? Yes?
So is memory like?
Go ahead. Okay.
Sorry. Is memory like like part of the closure?
Yeah, so we'll get that in a moment. Yeah.
Is the first block necessary because you say bar memory? Or
I'm sorry, can you just tell me which block, which
right
line?
under rec catalan?
Line 6.
Oh, is that block even necessary? Yeah, syntactically it's a little tricky because I need to put multiple things. Yeah. Okay. And it's sort of safer to just put blocks around here because we've got several things going on. So, okay. All right. Okay. Questions so far? Questions? Oh my God. Yeah.
You're missing an end after.
I'm missing an end. Where am I
For
missing
your
an end?
cases.
I'm missing an end for my cases. Okay. Thank you. Okay. Reindent. Okay, good. Actually, let's see what happens if we don't have that, okay? Okay, so that's our indication that we're missing an end. Okay, okay, good. Hand up there. There's a hand up there, yeah.
Slightly, but if you have more
memory, does every time you change memory, does it need to be a list? Like, is the type of var always
No, var doesn't care at all. Var is just, all var is saying is, the thing that I'm following me, the variable that's following me, is a variable as opposed to essentially a constant declaration. Okay? So technically in programming languages, we use two different words. We use the word identifier and variable. Identifier means it's just a name for something. A variable means it's a name whose meaning, associated meaning can change. Until now, everything you've written has actually been an identifier, in that it just identified a value with a particular name, and it couldn't change its association after that. With var, it can now change. Okay? Yes?
Would lines 22 through 25 need to be in a block?
22 through 25. Yeah, they do need to be in a block, don't they? So I could put the block over there.
Oh boy.
I don't know, I think that works, yeah.
Is there a way to bind, like, if you're to a variable to a specific type, like ensure it only has that type?
Yeah, if I put a type annotation on it over here, just like I could before.
Okay, cool.
Okay, so the same way I could do the same thing here. Okay, yeah.
But it's weakly typed otherwise, like if you could change memory to be 2.
So there's two pirates, right? There's the pirate with and the pirate without the type checker. So pirate without the type checker, well, even then it would still give you an error, because if I said put a list annotation here and you try to put number in there, it would give me an error.
Without annotation.
Huh?
Without annotation.
Well, without annotation, it has the, like, it doesn't, it's not even, it's so first of all, I reject the phrase weakly typed. You'll have a hard time defining it. Okay? But there's no annotation, so what is it supposed to be enforcing? There's nothing for it to enforce. Right? You didn't put an annotation. If you want something, put an annotation on. Yeah.
Can we create a variable without like, initializing the value?
No, then what? Then if you try to use it, what's it supposed to do? Yeah, yeah. This is like a sane programming language. Okay. Okay. That's what option types exist for. Okay. So seriously, for those of you who programmed before, that's why option types are the smart idea. So Tony Hoare created this idea of what's called null. So Tony Hoare is also the inventor of quicksort. And he gave this very famous talk, which he called his $1 billion error. And he said, adding null to programming languages was the stupidest thing I've ever done. Right? Because the thing is, the option type is an explicit declaration that I don't know what the value is right now. There are times when I'm not sure what the value is going to be, and there's this initial state before the thing is achieved quiescence, right? Like I don't know what to put in there. Put a none in there. Why is that a better discipline, for those of you who programmed in, say, Java before, why is that a better discipline?
At least you know the value if there's something.
You can't accidentally use it. You have to write a cases that says, am I in the none case or am I in the sun case? Right? So for things for which you did not need that initial state of undefinedness, you don't pay any price at all. For things for which there was a possibility that the value is not well defined, the option type basically is the language checking for you that you didn't inadvertently use the wrong value. Right? In Java, people have gone and built nullness checkers. That's called an option type checker, but through heroic like reverse engineering, because they have to kind of guess whether you're trying to use null in a bad way or not. Right? So other languages like TypeScript have said, look, this is a crazy idea, we should never let this happen. So they let you write null, but they're letting you write option type in the form of null is none. Okay? And if you try to use it without a proper guard, it'll blow up on you. So it's not really a null like Java's null. Right? So we've learned in pre-L design that this was just a bad idea. It's a historical artifact and it was a bad idea, don't do it again. So in Pirate, yeah, if you want that, write a none, and when you want to use it, just make sure you guard it properly. Okay? Questions? Yes?
When you...
By the way, none of us, we haven't checked whether this runs or anything. Just I mean, I'm glad. Your confidence is charming, but yeah.
When you make a variable, do you have to initialize its value to something?
Yeah, that was the question, right?
Oh.
Yeah, you have to. Otherwise, what's Pirate supposed to? What's it supposed to put in there? If I leave it like that, what is its value? It's not my problem as the compiler writer to figure out. Your damn problem. It's your program. You put a value in there. Okay? Yeah. Next question. Any other questions? Should we try running this? Yes? Okay, ready? Okay, at least we have a valid program. Passes one test case. Okay. Do we dare?
50.
Now try 50.
Do Catalan of Catalan 12.
What was the pause? What was the pause? Sorry? Well, that's not interesting.
Oh.
So
Oh wait.
The pause was that in computing that number. Arithmetic takes time. So, we have made an assumption this semester that if it were actually true, would destroy all of cryptography. Our assumption is that arithmetic took constant time. It does not take constant time. Okay? Arithmetic takes time. Now, traditionally, computers have used like 32 bits or 64 bits, and that's effectively constant, and it's fine. Arithmetic in that model takes constant time. Pirate will use as much memory as you have. It's like, look, you've got like, a gig of RAM or something, and why should I limit you to 32 bits? That's madness, right? So it will compute as much as you want. I'm not sure I want to type Catalan of 12, but maybe I'll do Catalan of
That's less than
that's less. No. Okay, 8. Fine. Okay, it's gonna take a while. Okay. So the problem is it takes time and space to represent numbers. Okay. If you represent arbitrarily big numbers, it's going to take space to represent them, and it's going to take time for them to compute. All right? Yes.
Alright, when you do Catalan of Catalan, does the outer Catalan store everything the inner Catalan?
So hold on. Okay. All right. Okay. So let's go back to this. It's instantaneous. Okay. So let's try Catalan of something smaller like 5. Okay. What was Catalan of 5 again? 42. Right. So that's well under 100. So the inner Catalan of 5 is producing 42. The outer Catalan is Catalan of 42. Have we seen Catalan of 42 before? Yeah, because we did Catalan of 100, right? It's instantaneous. Because all of the Catalans, right, are sharing that same memory over there. Okay? So another thing I could do is put this out here. Okay? So let's try Catalan of 100, fresh. Okay, so what's memory? Because I ran the test case down there, right? So that was actually the point I was trying to get to is you look at that Catalan of 5 over there. So if you look at the memory, it's telling you 5 is bound to 42, 4 is bound to 14. All of the sub values are already in there. Okay, so now if I run Catalan of 100, okay, let's see how long it takes. It's only got 5 values pre-computed. Ready? Really fast. And what's memory look like?
Oh no.
No, it's fine. It's fine. It's just got all of the values. They're all sitting there. Right? So now if I say Catalan of 100 again, it's just looking up that value. So if I say Catalan of 5, it's looking up Catalan of 5 in memory and looking up Catalan of that again in memory, right? It's just that I put memory out here instead of in here so you could see it, but if I put it in here, it's the same. What if I put what if I did that?
No.
It would be equivalent to.
That's pretty fast. Pretty fast.
Do 100. Do 100.
Okay, so you see the problem, right? Every time it's redefining memory and it's not remembering anything at all. Okay? This was the same problem we had with the counters. If I put it in too deep, it's a problem. If I put it out too far, everything shares the same memory, which in this case is kind of harmless, and I need to put it right in the middle. Okay? Actually, I don't need to put it right in the middle for this program. For what I'm going to do next class, I'm going to want to put it right in the middle. Okay? So there's actually a problem, right? So let's do this. Let's put Catalan out here. So this is now a software engineering point I'm going to make. Okay? So let's do Catalan of 100. Okay? And it's great. Okay? Now, let me do the following. I can, and let's not even do that. So here is memory. Okay? Well, memory is just like an exposed variable now. Right? I could go in and say memory equals empty. Right? And memory is empty. And I could say Catalan of 100. And it's great. Okay? But here's the other thing I can do. I could go and say memory is a list where I associate Catalan of 1 with 0 and Catalan of 2 with 0.
Oh,
Right? What happens now if so here is my memory, and now I say Catalan of 3. What am I going to get? Catalan of 4. Catalan of 100. I've completely polluted it. So, this is an important software engineering point. When you start to build larger systems, you need to make sure that you have properly kept control of the data that you need. If you leak it out too high, it becomes possible for other people to corrupt your data. And these are actual problems that you run into in computer systems. Sometimes, for example, people put private keys in places they shouldn't, and now somebody else can come and modify it, and now you're running against this thing that you trust, and it turns out that somebody else has taken control of your system, right? There are lots of bad things that happen in software engineering when you make things visible in a broader scope than you should, right? Just a general software engineering principle. So that's the real reason why, that's one of the two reasons why you really don't want memory to be there, you want it to be here, okay? So now I can do this and there's nothing anyone can do to harm me, okay? It's my private thing, but if I type memory, nobody can see it, okay? But there's going to be one more reason that we'll get to next class, okay? And that's the really beautiful reason. Questions? Before we leave, any questions, thoughts about this, about what's happened so far? Good? Yeah? All right, see you next class.